Welcome back. We are on part 2 of the neoclassical growth model. Remember last time we went through the setup of the neoclassical growth model. We covered some of the assumptions. We looked at like the utility function. We looked at the constraint, and we formulated either a Bellman equation or a two-period model. Either one works in the context of this course. Now, if we were doing something that was a little bit more mathematically rigorous, if this were like a graduate, like a master's or a PhD level macro course, you couldn't be using the two-period model as if it was equivalent to dynamic programming, because technically speaking, it's not. But in the context of the course that we're taking, it's sufficient. It's more than sufficient. So just, keep that in mind, I guess, if any of you decide that you want to go to graduate school for this stuff. That would actually be pretty cool if you did. It would be well worth your time to go to graduate school for economics. It's a lot of fun. It was 6 of the best years of my life in graduate school. That was fun. Anyways, so what were we able to do with the Euler equation? Well, it told us what the marginal utility of consumption today with the marginal utility of consumption in the next period weighted by the expected return, right? So that gave us like a consumption savings decision, like a solution to the consumption savings problem, which can then give us a sequence of policy functions like CT star, CT plus 1 star, CT plus 2 star, all that would maximize the agent's utility over the infinite horizon. So what are we going to do in this lecture? Well, we're going to write out the general equilibrium. We're going to find the steady states of the model. And then for the steady states, we're going to compare that to the Solow growth model steady states. And we're going to see why the neoclassical models contributions are, if you buy into this stuff, it's an improvement on Solow's work. And if you don't buy into it, which, you'd have to have a valid reason to, I guess. But if nothing else, we can at least see how it's different. And, we can make our mind up for ourselves as to which one is better. So we had the Euler equation, right? You will have seen this ad nauseum by the end of the course, I promise you. You'll be able to recite this thing in your sleep. It's 1 over CT equals beta times 1 over CT plus 1 times the marginal product of capital less depreciation. And this tells us the optimal intertemporal choices between today and tomorrow, or really today and like the next period. It doesn't have to be tomorrow. But for the next period, it would be for the period after that, and the period after that, and so on and so forth. So we need to list out the other equations to see the equilibrium and then close out the model. And when we're closing out the model, what I mean is we're accounting for every variable that's in the model. Nothing's being left out, right? So this part's actually pretty easy for us. It's just like, okay, list all the equations. There we go. Boom, 1, 2, 3, 4. It's all the equations. Have the Euler equation, we have the resource constraint, we have investment, and we have output. Now, you're like, okay, equilibrium, like general equilibrium, wouldn't that mean there's like a supply and demand, and then, like maybe some kind of like supply and demand for like capital, because you can choose to buy capital, and what is all that stuff? I hate to break it to you, there's no prices in the model. So if there's no price in the model, you can't have like supply and demand, like price and output space, because we just have output, right? We don't have prices here. Now, we could have prices in the model if we wanted to, but then it would be a little bit of a different model. When we get to business cycle models especially, we'll be seeing some of these models with price in them. And by that point, you will not have to solve any of them out. It's going to be one of those, I solve them for you, and you see the equations, and you just play with some of the equations. By that point, it's a little bit more plug and play than it is like actually deriving stuff, because I'll have assumed, you already know how to by the end of this section. Anyways, enough rambling about that. What equations do we have? We got the Euler equation. We have resource constraint, investment, and output. Now, technically speaking, there's one additional equation that we're missing here, and that would be an equation describing the evolution of technology, or A. It would follow what's known as an autoregressive process. It's really just for the econ nerds that'll stumble on this video, just so that they're aware for the sake of completeness. that, there is something else that kind of should be here. But in the context of this course, this is, an undergraduate, intermediate level macroeconomics course. I'm not going to make you guys do any of that stuff. That's really kind of like asking a lot of you guys. So the reason we want to write this out is we want to see how the entire economy like responds to stuff. And the more complicated the economy gets, like, so the more players we have, the more markets we have in the economy, the more equations we're going to need. And as a rule of thumb, you want to add 1 or 2 more equations for every new market we add in, because we still want to be able to close the model out. For every variable we have, we want to add another equation, right? So if you remember, like, algebra 2, I think it was in high school, at least it was when I was in high school, like, 35 years ago. I said that to be like as if 35 years ago is a long time, but like I was in high school. The amount of time it's been since I was in high school is actually getting dangerously close to that. So when I was in high school back in the Stone Age, that feels a little bit better to say. I think it was algebra 2 where we did this, where you'd have systems of equations. So if you'd have 2 equations and 2 unknowns, you could uniquely solve for the 2 unknowns. If, say, you had 2 equations and 3 unknowns, you could uniquely solve at best for 2 of the unknowns, and the third unknown would be parameterized in terms of some linear combination of the other 2 unknowns that were uniquely solved for. So if we have a system with as many equations as we have unknowns, the system is what's known as identified, right? Because we can identify every single variable. If we have more unknowns than we have equations, then it's what's known as under-identified. And if there are more equations than we have unknowns, then it's referred to as over-identified. And, over-identified systems really aren't necessarily a bad thing, especially in the context of models like this, because we can then parameterize, like, say, some of the moments in the data that these models generate, and then see if the remaining moments we didn't try to parameterize get generated similar to what we see in the real world. And by moments in the data, I mean things like, the mean, right, or the standard deviation, things like that, which we'll learn a little bit about when we get to the real business cycle model. We'll kind of cover how well the real business cycle model captures some of the moments in the data. And what's interesting is the real business cycle model is actually just an extension on the neoclassical growth model. It's like taking the neoclassical growth model and turning it from a growth model into like a business cycle model. But that's, I don't know, at least a month away. So we did the general equilibrium. Good for us. Let's do the steady states, right? So just like in Solow, we wanted to get the model into a steady state so that it's at rest. And then when it's at rest, we can see what the entire system's doing when we want to start imposing shocks. And what we can also do, which we won't be doing here, but we can if we want to, I guess, although we don't, is we could calibrate the model using like real data and then see how the responses to the shocks look. And then what we could also do, and this is like more graduate level stuff here, what we could also do is then generate like an empirical model using similar variables, but variables that have been like observed in the real world. And we can see if the shocks the model generates as calibrated using real data fits an empirical model fit with, real data, and see if they match, right? And if they do, then the model's good. And if not, well, then the model sucks and it needs work. For the most part, every model has issues. Every model is wrong, but some models are useful. So whichever model you're looking at, it's going to give you some results that suck, and it's going to give you some results that are very useful and meaningful. Because, no model is perfect. So anyways, steady states. What are we going to do first? Well, we want to get steady state capital first, just like we did in the Solow model. And steady state capital is very easy to get here. We're going to start with the Euler equation. Now, in the steady state, remember KT plus 1 equals KT for all t, and the same would hold for consumption, output, and investment. So, okay, in that case, I'm going to set the t and the t plus 1 subscripts to SS. So I have my Euler equation now expressed in the steady state. And then What I want to do is I want to solve for capital. So I want to put everything that's not capital on one side of the equation and everything that is capital on the other side of the equation. So I'm just going to isolate that KSS. So I multiply both sides by CSS. Okay, well, that gives me equation 7 here, which is the Euler equation, just with consumption on one side of that equation. But CSS divided by CSS, well, CSS and CSS are equal, right? 1 over 1 is 1, 2 over 2 is 1, 3 over 3 is 1, CSS over CSS is 1. So, okay, the left-hand side of that reduces to 1. And then what I can do, right, the next thing that I can do is I can divide both sides by beta, because beta is being multiplied by everything in those parentheses. So divide both sides by beta gives me equation 9. Okay. What's the next thing you think? What would be the next thing we want to do? We want to divide by something, or do we want to subtract something? Personally, I think I would want to subtract something. I'd want to subtract that 1 minus delta. Right, so it gives me 1 over beta plus delta minus 1 because, well, addition and subtraction and stuff. And now that's equal to alpha times a times k to the alpha minus 1. Divide both sides by alpha times a, and that gives me 1 over beta plus delta minus 1 over alpha times a, and that's equal to KSS to the alpha minus 1. But here's the thing, right? While alpha is just kind of could be anything, almost anything, actually not close at all to almost anything, it can only be a number between 0 and 1, right? So alpha is positive, but it's less than 1. So let's say alpha is equal to 1/2 for a second. Okay, what's 1/2 minus 1? That's negative 1/2, right? What is that? Well, negative 1/2, that would be 1 over the square root of KSS. You don't want that. Why don't we want that? Because KSS would be in the denominator there. We want KSS to be the numerator. So if we want KSS to be in the numerator, what do? Well, if we raise both sides to the power of negative 1, which we can do because, equations and stuff, what I do is I flip the numerator and the denominator. So I'm going to do just that. I'm going to flip the numerator and the denominator, and now the exponent becomes 1 minus alpha instead of alpha minus 1. So I raise both sides to the power of 1 over 1 minus alpha now, and that gives me steady state capital. But this is still a little messy looking. All right, equation 14's a little messy here. What can we do about this? Because the numerator inside the left-hand side, that's nice and simple. It's just alpha times a. All right, it's just 2 numbers. The exponent isn't bad. We've seen that before. It's just 1 over 1 minus alpha. And once we know what alpha is, once we get a number given to us for alpha, well, that just reduces down to 1 over a number. That's not too bad at all. But it's the denominator on that left-hand side that's kind of screwing with us. That 1 over beta could maybe be a little bit better. And then we got that minus 1. Delta's fine. Delta's going to stay where it is. But it's that 1 over beta and that minus 1. So what's beta? Well, beta, remember, is a measure of how patient we are. But beta was equal to something. What was beta equal to? Do we remember? Maybe you want to take a minute to remember. I would say push pause, but I have no guarantee you'll push pause. So instead, what I'm going to do is I'm just going to keep talking and sort of keep things chugging along for now. What was beta? Well, beta was equal to like a fraction of something, right? Like 1 over, what was it? Like 1 over 1 plus rho, right? Yeah. Cool. Beta is equal to 1 over 1 plus rho. Now, beta is a measure of how patient we are. It tells us how much we value the next period relative to this period. So if beta is 0.95, the next period is 95% as important to us as today is. So if beta goes up, that's a good thing. We're getting more patient, right? What about rho, though? If rho goes up, what does that mean? Well, rho is a measure of how impatient we are. So if rho goes up, we get more impatient, and then because fractions, if rho goes up, beta gets smaller, beta goes down. Okay, cool. So I'm going to plug that in. So now I get alpha times A over 1 over 1 over 1 plus rho plus delta minus 1 to the 1 over 1 minus alpha. Now, that looks kind of stupid. Right? And maybe less stupid looking form, maybe we could have something like this, because 1 over 1 plus rho would just be 1 plus rho. So, okay, well now I got alpha times A over 1 plus rho plus delta minus 1 to the 1 over 1 minus alpha, and that's equal to steady state capital. Well, I can clean things up in the denominator a little bit, because I got a 1 and a minus 1, right? Well, 1 minus 1 is 0. So now I just got alpha times A over rho plus delta to the 1 over 1 minus alpha equals steady state capital. That's our steady state capital. So if at any point in a homework, which will, come sort of soon, or at any point on like an exam, if it's covering the neoclassical growth model and it's asking for steady state capital, I'm telling you right now, it's equation 18. So if at any point you get a question, what is steady state capital? If alpha is this and A is this and rho is this and delta is that, what is KSS equal to? Well, look at equation 18. You don't have to derive equation 18 for me, right? You might have to derive the Euler equation, but you're not going to have to derive steady state capital. I showed you how I got it, kind of as a, hey, look, told you I know what I'm doing. But steady state capital is steady state capital, at least in the neoclassical growth model. Now, it's going to be, it might be a little different in other models depending on what we got. But here, it's just alpha times A over rho plus delta to the 1 over 1 minus alpha. Always, always, always for the neoclassical growth model. So we can get steady state output first. I guess I should really say next because we got steady state capital first. But, it's really pretty easy because if we know what output is in the steady states, YSS equals ASS, that's a wordy dirt, times KSS to the alpha. Oh, and just put KSS into it. Okay. It's A times alpha times A over rho plus delta to the 1 over 1 minus alpha times alpha. But then that alpha, just multiply that through the exponent, and I get YSS equals A times alpha times A over rho plus delta to the alpha over 1 minus alpha, which kind of looks like what we saw in the Solow model. And then again, it kind of doesn't. But let's get steady state consumption and steady state investment. We'll do steady state investment first because that's pretty easy. Remember, investment's the law of motion of capital, which in the steady state is just equation 23. It's equation 22 with SS subscripts instead of T and T plus 1 subscripts. Now I can simplify it from here because if I distribute KSS through that 1 minus delta, I get KSS minus KSS plus delta KSS. Well, I got KSS minus KSS. Cool. That means I got 0. So now it's just ISS equals delta times KSS. So now what I'm going to do is I'm just going to plug KSS in for that one KSS that we have in equation 25, and that gives me this. Delta times alpha times A over rho plus delta to the 1 over 1 minus alpha. Hey, that's not bad at all. It's just steady state capital times delta. All right. Well, that just leaves consumption. Now, consumption is going to be a little long and messy. But that's really just because I'm lazy and I don't want to simplify stuff. And you're not going to have to simplify stuff either. I'm going to take the resource constraint in the steady state. It's just this. Well, if output is the sum of consumption and investment, then consumption is the difference between output and investment, right? So it gives me equation 29. And I just plug in steady state output and steady state investment. And that gives me equation 30. Here's a little spoiler, right? You're probably not going to have to do anything with steady state consumption. It's probably more like steady state capital and steady state output. The rest, maybe it's important to know, I guess. You're probably not going to have to do anything with it. But in the event you do, in the event I change my mind or something, right? Steady state consumption will be what you see in equation 30. So on a homework or an exam, steady state consumption is what you have in equation 30 there. Again, you don't have to derive it. If you just cite it. This is the formula, and then you plug stuff in for the formula. I'm happy enough as it is. So that was steady state consumption, right? Well, steady state investment will be what you see in equation 26. Again, don't have to derive it. You can just say, hey, from the book or from your lectures, it's this thing. And you just plug that, just put that on the homework or the exam and just plug stuff in, and there you go. Right? Steady state output, equation 21, will always be that if it's a neoclassical growth model. Always. And then finally, steady state capital, equation 18. So equation 18, you might want to write this down. Equation 18, equation 21, equation 26, and equation 30. Those equations will be very useful to know. Write them down. If you see a homework and it asks what it is, write it up. There you go. So let's compare the steady states of the two models that we've learned so far. I've had Neoclassical and Solow. Solow's was S times A over delta to the 1 over 1 minus alpha. And Neoclassical is a little different, right? It's alpha times A over rho plus delta to the 1 over 1 minus alpha. So it's kind of similar, but then again, it's kind of different. The form is similar enough. Well, I guess that's to be expected because they're both Cobb-Douglas production functions. So in the steady state, you're going to have a lot of similarities. Now, the exogenous variables that the endogenous variable is expressed as like, a function of or whatever, yeah, that might be a little different, but it's going to be something to the 1 over 1 minus alpha, right? So let's look at this. Well, we had S in the Solow model, savings. We have alpha in the neoclassical growth model. They're not really the same thing. Actually, they're not the same thing at all. They're related, though, right? Because savings is assumed in the Solow model to be just a constant savings rate, right? So if savings is constant, well, there's no consumption saving decision to make because it's kind of already been made for us because it's exogenously chosen. Here, saving is endogenously chosen by the agent. It's chosen by us, right, if we're solving the model out. So, right, we can't really have S in there then. What is A? Well, A, remember, is capital share of output. Think of it like this, right? It tells us how, it plays a hand in telling us how productive an additional unit of capital is. So the more productive capital is, the higher the return on capital, so to speak. Well, if you're going to get like more of a return on capital, maybe it's beneficial to invest more capital, right? If you get more out, you're going to, probably going to want to put a little bit more in. So, we got that. Now we've got A in the numerator for both steady states. Technology, right? Technology's good. Now remember, with the Solow model, I'd said anything in the numerator for steady state capital was a good thing, right? Anything in the denominator was bad. Because if the denominator gets larger, the whole number gets smaller, right? If the numerator gets larger, the whole number gets bigger. So because fractions, anything in the numerator is good, anything in the denominator is bad. So for steady state capital in the neoclassical growth model, we've got rho plus delta. Delta's bad because it means shit's falling apart, right? We don't want that. Less stuff falls apart, the better we are, the happier we are. Because that's less you got to put in to replace it. But then we also have rho. Well, rho wasn't in the Solow model because, again, there was no explicitly modeled household in the Solow model. Savings was exogenously chosen, and it was constant, so rho would have played no part, right? Rho is just equal to 0, I guess, in the Solow model. Actually, it's even worse than equal to 0. It's just not even there. Well, I guess, if it's 0, it's not there either. So, okay, well, I'll just put my foot in my mouth. So you got alpha times A over rho plus delta. Alpha and A are good. Rho and delta are bad. Rho goes up. You get more impatient. And if you get more impatient, right, you want to consume more today and you want to save less because you don't care about the future as much anymore. So if you want to consume less, well, that's fine. Or sorry, if you want to consume more and you want to save less, that's fine. You buy less capital. And if you're buying less capital, well, then steady state capital falls. Okay. So yeah, Rho is included in Neoclassical, not in Solow. And if we include for Rho, well, then we've got the household kind of like the household's preferences playing a role in determining what the steady state is. Now, by having that, right, remember we're accounting for the individual preferences in the model. So instead of it being like this top-down approach, which we had in the Solow model, where we assume the macroeconomy works independently of individuals, that's kind of a bogus claim to make if you think about it, because the macroeconomy is just like an aggregation of a bunch of microeconomies, right? People make decisions. People's choices matter. People's choices affect the equilibrium because remember, economics is all about unlimited wants against limited resources. And it's the choices we make that determine the state of the economy, determines the equilibrium that we're in, or the equilibria, really, because multiple equilibria, right? So if we got that like at the micro level, the macro level is that just bigger, just at the macro level. So we're assuming with the neoclassical growth model that it's composed of a bunch of people who all make choices that affect the economy. So if we incorporate their preferences into steady states, it means when the economy is stationary, right, or when it's at rest over time, then at least some of the determinants of it come from the individuals in the household. It's just if we solve one individual's choices and that individual is assumed to be representative of the whole economy, well, you can kind of solve everything out and go, all right, well, that's what one individual does. And if, the economy is made up of 330 million individuals, okay, just multiply by 330 million. Boom, there you go. So, with this, a lot of things are different, right? We also have alpha in the numerator instead of savings, and alpha is capital's share of income, right? So the total income generated would be y equals a times k to the alpha times l to the 1 minus alpha. Alpha is the amount of income that's generated by capital, and 1 minus alpha would be the share of income generated by labor, right? But this is all per capita that we had here. So, it's all like units of capital per effective labor unit. So the amount of income that capital generates helps determine the steady state capital. Yeah, it makes sense to me. If it generates more income, you're going to want to increase your capital holdings each time period, right? And then in the denominator, well, we had just delta in the Solow model. So if delta increased, steady state capital falls because you need to put more capital into replacing the stuff that fell apart. And if you're doing that, well, it's like you're spending more resources just to keep what you already have. So it's less that's really hanging out in steady state because you got to put more and more and more effort, more and more resources into fixing the stuff that you already had rather than adding new stuff. Now in neoclassical, we also have that rho term. So if rho goes up, you get more impatient and you care less about the future. So if rho increases, beta falls because fractions. And in that case, the denominator gets larger, the numerator stays the same, and beta falls as a result. So when rho gets bigger, you get more impatient, and you're willing to give up your future happiness for current happiness. It's probably, poor form to be referencing getting drunk, but screw it, right? We're all adults. Think about like getting drunk, right? If you want to get drunk tonight, what are you going to do? You're going to go out and party, have a lot of fun tonight, right? You're going to have an absolute blast. And you say, screw it, I'm going to deal with the hangover tomorrow. You're willing to pay the price for it tomorrow. So on, say, Saturday night or Friday night, or, if you're really, really into partying, say Wednesday and Thursday night, right, you might have a smaller beta than you'd have on, like, say, a Monday morning. You want to get drunk tonight, that's fine. You're valuing your current happiness more than tomorrow morning's happiness, right? Think of it like you're borrowing happiness from tomorrow. You get a lot of happy tonight, but you get a lot of unhappy tomorrow when you're hungover and you're not feeling that great. So if you consume more now, right, there's less to consume in the future. So you invest less capital and steady state capital falls. And by having individual preferences, right, by having the household's preferences, we can explain more of the movement in the macro data with additional variables that we can actually see in the real world. We can figure out what rho is by looking at real world data, and we can see that delta may not play as much of a role in this model as it does in Solow. So what do I mean by that? Well, what I mean is Solow may have overestimated the effect of delta in steady state capital. Because if the steady state capital for the neoclassical growth model is to be believed, and not the Solow's, like the Solow's form of steady state capital, the denominator would be rho plus delta in the neoclassical. But Solow's assuming it's just delta, in which case depreciation in the Solow model is actually picking up the effects of not just depreciation, but also the household's impatience. Because remember, we want to fit all this stuff to real world data. So if we're not parameterizing the theoretical model correctly, well, the way it fits the real data is going to be all screwed up. So we need to have some kind of measure for what rho is. And depending on what, we think rho is, and there have been, studies that would estimate what rho is or what beta would be, things like that. Well, really, I guess if you know what one is, you know what the other is. When you have that, well, now delta's not playing as much of a role, and we're not overstating the effect that delta plays. Right? Because if you got the depreciation of capital, you don't want to say it's greater than it really is, because if you're saying depreciation is greater than it really is, but then you look at the real world and you go, wait a minute, depreciation is not 10%, it's 5%. Right? Just I'm pulling numbers out of thin air. But if Solow says it's 10%, but the real world data is telling you it's 5%, then what the hell's going on? Well, what's actually going on is that delta in the Solow model would be really equal to like rho plus delta for the neoclassical model. So rho would be that missing 5% that we thought was for capital, but it's really not. Okay, enough about that. We're going to look at two shocks in this model, A sub t and A sub t plus 1. Now, you might be like, well, they're the same thing because it's technology today or technology tomorrow. Oh, but you would be wrong. Let's look at our equations here. The Euler equation describes how the agent chooses optimally over time, right? It can be used to get us a demand function. It's not necessarily a demand equation because, again, there's no price here. But you can kind of think of it as like a demand-ish type thing, right? So if there's a shock to something in the Euler equation, it's a demand-ish side shock. Why? Because, well, that's the household's decision, right? It's the household's decision-making. It's, the household deciding how much to consume or how much to save. Those sound like demand-side decisions, right? How much do you want to consume? Well, if you want to consume more, you buy more stuff. If you go buy more stuff, that sounds like a demand shock, right? You all of a sudden you want more things. Okay, so a shock to AT plus 1 is a demand side shock. But take a look at where AT shows up, right? It shows up in one other equation, well, in just one equation, in the general equilibrium that we were looking at. Which one does it show up in? You take a minute to flip back if you want, flip through your notes, flip through the book, whatever. Well, play Jeopardy music, but I'd probably get hit with like a copyright thing, which I guess doesn't really matter. I'm not exactly trying to get monetized here anyways. But okay, so there's a shock to A. Where does A show up? Well, it shows up in the production function, right? Things that get made. If we're looking at a function for things that get made, that sounds like a supply side thing to me, right? So a shock to AT is a supply side shock. A shock to AT plus 1 is a demand side. Let's do AT first, right? It shows up in the production function. So it affects production first and everything else after, right? Because, where it shows up first, what the equation it shows up first in is the equation that's hit first. So A sub t would go up, right? Which increases production. Why does it increase production? Well, it means we got some sort of technology that allows us to produce more using the same amount of resources as before. Right? In the Solow model, when I was talking about what the shock to technology could be, I gave a number of examples, right? I gave, I think the cotton gin, because really, when I think about it, like that's the first thing that comes to mind. Is it's like, okay, we got the same amount of capital, right? Same amount of like cotton that goes in. You got the same amount of people working the cotton gin. It just means you can churn out cotton faster. You can do so more efficiently. But there are all sorts of other things. The invention of the computer chip, right? That thing was fantastic. So, if you have a computer that is pretty okay, but then you get a better computer, right? Well, that's a technology shock. You can do more with fewer resources. It takes, less time to do these things. And really, if we're looking at computer stuff, it's really kind of in terms of like computing time these days, which is relatively cheap, but it gets cheaper as we go on. So long story short, A goes up, production increases, output goes up. So when output, Y, goes up, it's also affecting the resource constraint. So if output goes up, right, we can then expect to be able to consume and invest more, or some linear combination of those two would be going up. Now, of course, that's entirely dependent on the household's preferences established by Rowe, but consumption and investment would be expected to increase. Now, the preferences over consumption and savings would, like I said, determine how much each goes up if both actually go up. But it's likely CT could increase so much that I would want to fall. But we're not really going to be considering that in this class. Instead, I'm just going to assume C and I both go up. Now, if we had like a different functional form for the utility, yeah, you could probably have a case where I could fall, maybe, I guess. But actually, I don't know. I think you could. I believe you can. Don't take my word on that though. But yeah, here we would just assume that C and I both go up. So consumption goes up, investment goes up. We can consume more today, right? We get more that we can consume with because, if you think about it in terms of like price and output space, things get cheaper. Technology goes up. We can make more things with the same amount of stuff that we had before. So we get more things. When more things hit the market, the price of those things falls. So we can consume more stuff. So because A goes up, the marginal product to capital increases, meaning CT plus 1 also goes up. So the supply shock ultimately does affect demand, but it does so like indirectly in second, not first. So if A increases, C increases, CT plus 1 increases, IT increases, which then implies KT plus 1 increases. Now you're probably going like, well, what does that mean about KT? Well, KT doesn't move because KT was chosen yesterday. So that's already set in stone. KT has already been determined. It can't be changed, even with an increase to technology. So that was for the technology shock, like the current period technology shock. What about future technology? All right, AT plus 1. Well, this shows up in the Euler equation first, which affects demand first. So a shock to A sub T plus 1 is a demand shock. Now, when A T plus 1 goes up, households are expecting tomorrow's output to be higher. And thus, there would be a higher marginal product of labor. So it means they think the marginal product of capital is going to be higher. The opportunity cost of not investing gets higher. So if the marginal product of capital, I don't know why I said marginal product of labor, it's marginal product of capital. The marginal product of capital is high, right? Then capital is low. And what would you want to do in that case? Increase the amount of capital in the economy. But households, back up. Households are going to buy less capital, consume more stuff now, which means KT plus 1 decreases. Now, when it falls, CT increases and CT plus 1 decreases. So when AT plus 1 increases, CT increases, CT plus 1 falls, investment falls, and KT plus 1 falls. Sorry, that one was a little wonky there. My mistake. So it happens when you have a really long day. So how does this hold up? Well, it holds up good and it holds up bad. For the good, it's micro-founded. It shows us how Solow's model is missing that key ingredient. but there's still a problem. It assumes growth is exogenous. It's saying growth just magically happens here, and there's nothing to show any sort of growth coming from like within the model. Because when we have economies in the real world, which we do, and they grow, they're not growing by chance. They're not growing like because we got lucky and the economy just says, "Hey, screw it. I want to get bigger today." No. You spend time investing things, right? It's maybe not necessarily just capital investment, although capital investment is good. Growth doesn't necessarily come from just capital investment. It comes from other things like human capital investment, right? It comes from ideas. It comes from us getting these ideas and then implementing them via the physical capital that we have. So if in the real world we're getting growth coming from our decisions, our choices, our investment in things, the model should be telling us something similar. Now, it's not always the case that the model has to completely and totally accurately reflect things in the world. We do make a lot of simplifying assumptions. But maybe, like just maybe, a simplifying assumption shouldn't extend to the source of growth. Because, well, if we just assume growth is exogenous, that kind of cuts short the entire argument for the existence of a growth and development subsect of macroeconomics. Be like, well, what's the point? It's exogenous. Boom, moving on. Solve that problem. And it's not exogenous. And we shouldn't be making a simplifying assumption that it is exogenous. So it doesn't really do a whole lot for the lack of endogenous growth, but at least it improves on the shortcomings in terms of the lack of micro foundations from the Solow model. Now, for endogenous growth, that's coming up in the next chapter. And then after that, we're going to look at human capital investment, and then we're done with this section of the course. So the next two models that we look at are just different extensions of the neoclassical growth model. The first one is looking at it's a basic endogenous growth model. And then the second one is a human capital investment model where we can actually have choices for how much human capital we want to invest. And in that case, it's kind of like a dynastic approach where it's like, okay, say, actually in this model, it's really not. It's sort of I want to invest in my own human capital, but a good way to really think about it is like investing in your child's human capital. You want them to be smarter and more educated than you are. But that wraps up. That's to be dealt with at another time. This wraps up the neoclassical growth model. And yeah, it was a little rough, I'm sure. Had to learn the dynamic programming stuff. We had to learn how to find the Euler equation. That, wasn't necessarily easy, although when you get enough practice, it does become easy. And there's another lecture coming up where we're going to go over some additional. We're going to get some more practice for dynamic programming. This hopefully by the end of that you'll be in pretty decent shape. But yeah, so here we got the Solow model. Wow, I'm getting tired. We got the Euler equation, and we compared the steady states to the Solow model. All right, that one sounded right. And we saw where it was good, and we saw where maybe it's not so good because we don't have exogenous. We have exogenous growth. We don't have endogenous growth. But this at least tells us where we can start to improve things, because maybe we don't want growth to be exogenous. Maybe we want it to be endogenous. But that is for the next lecture, not for this lecture. So thanks for watching, and I will see you in Chapter 8.